Okay, I'm going to talk as briefly as I can about image display. And the objectives here are talking about display parameters, and particularly understanding how and why we window and level our images. And then we'll look at applying that knowledge. So at some point I'll give us all an opportunity to come up here, manipulate CT images, window and level them some. X-ray techs, y'all get an opportunity to do that some in your lab. At Newton Med, if you're ever looking at a PET CT image, and you can actually window and level that, as well as kind of window and level SUV values, I think. And then we'll talk about ROIs, what these regions of interest are, what the standard deviation is for it, and we'll talk about some additional display options that we have, and that's kind of the main objectives here. So these window settings, these are the exact same images, right? We've just changed the way that they're displayed. One of these images shows an enhancement of lung tissue, and the other one shows the cardiac system more clearly. And so what she talks about in this textbook is because there is 2,000 different Hounsfield units, right? But most of our monitors can only show 256 shades of gray, plus the human eye can perceive even far less than that. What we're going to need to do is window and level to get all of the data that we can out of these images. Yeah, that's page 32 in our text. So, and here it is that's just reiterated here, that as a general rule, the human eye can't appreciate these contrast differences, but the computer can. So we need to window and level in order to make those contrast differences apparent. So we use a grayscale to display CT images, and that's true whether we're working with the data as treatment planning volumes for radiation therapy, or looking at them as the CT portion of a PET CT scan. It will always be represented in that grayscale. And that grayscale we've talked about is tied to the Hounsfield unit scale, which is directly tied to linear attenuation coefficients. Okay? So in this system, it assigns a certain number of Hounsfield units to each shade of gray. And in general, the higher the HU value is, the lighter the shade of gray. Right? So like 1,000 Hounsfield units is going to be white. Right? A negative 1,000 is going to be black. The very first thing that we can start to play around with then is window width. And one way to think about this is the window width is going to be most directly tied to the contrast scale. So if I have a high level of contrast, I will have a narrow window width. I'll say that again because this is something that students struggle with, and I even struggled with as a student. If I have high contrast, I have a low window width. We might think about that. Why is that? Well, what I'm saying is the width is like the number of little shades of gray here, right? And on the one side I have black, this negative range, and on the other side I have white. So if I have a narrow width, right, it's going to go from completely blacked out to some kind of gray to completely white very quickly, right? So we would call that high contrast. The high contrast is going to have a narrow window width. Conversely, if I want to turn down the contrast, right? So if I have a lower contrast, I will increase the window width. I will need to increase the width, right? And again, it's the same thing. I've made more little steps here, and I'm not going to sketch it all out here because I draw like a 5-year-old with this stylus. But I've just said I've increased this little thing here that goes from black to the various shades of gray to completely white. So there's lots of gray there. The window level is picking the center where we want these values to be displayed at. So the closest thing to think about window level might be the blacks and the whites. So if window width is all the grays, window level is going to determine those blacks and whites, right? So here we've got a window level of 0. The window level is 0 here, and the window width is 300. And now you say, well, wait, where'd you get 300 from? The 300, if I think I'm going to go half that distance in the positive direction and half that distance in the negative direction, right? So I've got everything from negative 150 over here to positive 150 over there. That's 300 Hounsfield units, right? So my center was 0. My width now is 300. Okay? Everything that's this side of 150 is going to show up completely white on the image. Everything that's this side of negative 150 will show up completely black. So here is a review question going from that. If the selected window width is 400 and the window level is 50, which Hounsfield units are going to be displayed on the image? And the answer is negative 150 to 250. Okay? So let's draw that out real quick so I make sure everyone's tracking with us. I'm just going to make a line because this is my Hounsfield scale. Okay? The window level, they've said, is 50. So here is a 0 here, which is water. And they've said it's 400. So how many Hounsfield units am I going to go this way? 200, right? 200 because it's half of 400. So that's going to bring me up to 250. And then how many Hounsfield units am I going to go this way? 200, and that's going to bring me down to negative 150. And there is the correct answer. Okay, one more little caveat here is just some general rules for messing around with window width and window level. The window level, as a rule of thumb, should be set to the area of whatever anatomy we're trying to look at. Okay, so for example, the one instance where we might set it to a negative level is if we're trying to look at lung. If we're trying to look at lung tissue, we might set the window level negative. In general, the window widths from about 500 to negative 2,000 are going to be the best for imaging tissue types that vary greatly. So we're going to try to see all of these tissue types within a single image. Okay. The wider the window width is, the greater the anatomic diversity that we'll see, but the subtle differences will be lost. And so because that wider window width decreases image contrast, they will also suppress noise. So the higher contrast images are going to look noisier, the lower contrast images will look less noisy. And
higher contrast, more noise?
Yeah, higher contrast, more noise. Higher contrast, more noise. So here's another review question for us. A window width of 90 is most likely used to display an image of what? Yeah. And so we're thinking about what level are we looking at, right? So for abdomen, we might look at like a window level of about 60, 50, 60. If we're looking at lung, we're going to want that level to be negative, right? If we're looking at bone, we're going to want that to be pretty darn high, right? And this is mapped out for us in our textbook. If you turn, there's a lot, star and underline and everything on page 36, this stuff, typical Windows settings. These are pretty great. These pretty much work for every possible CT system I've worked on. And they give you an idea not just of what the typical Windows settings are, but like we just demonstrated, it gives us an idea of what the kind of standard Hounsfield unit is for different things. So for example, I know that if I'm looking at the brain, I want to be somewhere around this 30. It said 90 in the last slide, but you'll notice that the width includes that. Okay. So this does give us a general idea of what the different Hounsfield values are in addition to window settings. Let's talk about regions of interest, or an ROI. It's typically circular, but it might be kind of elliptical shaped, and sometimes they're square, but they're drawn by the operator. You can drop them on CT images, on nuke med images, you can drop them on radiation therapy images, but it's going to allow us to measure particularly Hounsfield units within the region of interest. So what I'm saying is you can literally just draw this thing on the image and it's going to sample the Hounsfield units there. And we'll use it quite a bit. So it's important to think about, and if you need an illustration of what that looks like, on the top of page 37, she's drawn an ROI on the streak artifact from the teeth. You can see it says a little number 1. She actually drew that on there. There's also an ROI placed on the patient's right kidney in image C. So she sampled what the kidney Hounsfield units are there. And it's expressed down here at the bottom. There's a bunch of numbers that are given. One of those numbers is the mean, and the other is the standard deviation, right? And so that mean is the average value that we might see. So it's about the Hounsfield value of that tissue. And then the standard deviation is how much things vary from that average in one way or the other, typically positive and negative. And one thing to talk about with that mean versus standard deviation, the standard deviation can give me an understanding of how much noise there might be in this image, and also how well did I place my ROI. Like if I set the ROI kind of between to where I'm sampling both the kidney and whatever tissue is outside of the kidney, the standard deviation will be pretty high, because that attenuation value between the kidney and like the retroperitoneum is going to be pretty high, right? So I want to make sure I place my ROI right where I want it to be. Like if I'm putting an ROI on the aorta with contrast in the aorta, I want to make sure that it's right there in the contrasted aorta to get an accurate measurement. If I'm sampling, again, material in addition to the contrast, I'll get a larger standard deviation. We have a bunch of different things we can do with these images. We use distance measurements a lot. We can annotate the images and make notes and say, okay, the measurement here is approximately this, or this distance is this. We can create reference images, and she has an example of what a reference image looks like on the bottom of page 38. She has a lateral L-spine, and she's created this reference image using the scout image. She's overlaid where the different slices were taken, right? And this is very useful because now I have an easy way to see where I'm at in the z-axis on this other image. So I can say that is definitely, for example, L4 or whatever it is, because I don't need to run up and down on it. I can just look and see, okay, I can count down L4 right here, right? I'm just saying, for example. So these reference images are very helpful, especially if we're doing spine work, because it allows us to see, okay, that we're at the level of L whatever here. Whereas if we didn't have this reference image, we'd have to fly up and down the spine and try to orient ourselves. It can be very difficult. So a lot of protocols will call for those. We can magnify these images. We can minimize magnification. We can do multiple image display, and that's the way that we're typically used to seeing CT images. It's kind of 4 different screens with different images on them. And then some of the screens might be tied together to where if I move up and down on this screen, I'm moving up and down on the other screen too. Those are all some of the ways that we can display these things. We can look at histograms. And one of the things that she's talking about, and one of the ways that we use histograms is, and we'll talk about this more in the summer, but if we're measuring contrast and how it perfuses, we can set an ROI measure the histogram, and when it gets to a certain spike, we can initiate the scan. Okay, and I know I just threw a whole bunch of gobbledygook at you, but just understand that these histograms we can use to sample things in real time. The histogram, from a CT text point of view, can be used to sample things in real time, so it will be tied to certain protocols. And we'll come back to that in the summer. I'm not necessarily going to test you on that right now. Okay? And then, of course, we've got multiplanar and three-dimensional reformatting, which we'll get to at a later time.